This is our final unit where we discuss specific algorithms with cryptography and how they're used. So basically what tools we have available to us with cryptography, with encryption, and all these modern standards and when they're appropriate to use them. We also discuss public key infrastructure, PKI, and also certificates. We'll talk about certificates a little bit and how that stuff works, which all has to do with public key infrastructure. But it's important to understand certificates and how we use them and why we use them. I dispensed of all the fancy graphics in this unit because it's a rather long PowerPoint. I'm going to go through the PowerPoint pretty quickly just because there's a lot of information. And of course, the PowerPoint will be available to you in Blackboard, so you can certainly review it on your own time for your notes and to go back and reference it without having to go through the video and pausing all the time. But I am going to go through this rather quickly, so it's going to be a little different than the other presentations that we've done in this course. So public algorithms, the best algorithms are always public, and I talked about this a little bit in the previous unit. And why is that better? Well, first, they're peer-reviewed by other experts, both in cryptography and mathematical experts, and they can vet these algorithms to make sure that they're secure. If there's any hole or if there's any problem with these algorithms, the larger scientific community and cryptographic and mathematical professionals will find those problems. So publication is important since flaws in the system can be revealed by others before actual use of the system. So a system that maintains the security after public testing can be reasonably trusted to be secure. In other words, if everyone has access to these algorithms, there's so many people that are looking at them and vetting these algorithms that it's pretty certain that it's fairly secure if all of these experts all over the world have had access to it and we're able to see how it works. So first we're going to talk about hashes. I talked about what hashing is for before. This is one-way encryption. So this was when we verify the authenticity of a message, basically. So in the CIA triad that we always talk about in IT security, this would be the integrity part of the triad. So three things we're going to talk about. We're going to talk about hashing functions in general. We'll talk a bit about collision attacks, which is a known way to attack these algorithms, and then common hash algorithms that are in use today. So let's get started with this part. So hashing functions. So hashing functions are commonly used encryption methods. We'll talk about this in a little bit more detail, but a hashing function is a special mathematical function that performs one-way encryption, which is what I talked about in the previous lecture. I talked about how if we take plain text, put it through a hashing algorithm, we get ciphertext, but we don't get ciphertext from the plain text, so we can't go back the other direction. So it says right here, there is no feasible way to generate two different plain texts that compute from the same hash value. So two popular hash algorithms that we discuss in this course are SHA, or SHA, and MD, or message digest. And there's different versions of these, which we're going to discuss. So here's just a graphic that basically shows you a hash algorithm. Again, we kind of looked at this in the previous unit, but you have the original message in plain text. You add some padding because hash functions generally block encryption. So we break the data up into evenly sized blocks, which I'll talk about in just a minute. You put it through the hash function, you end up with your message digest, which is really the fingerprint of that message. So there's really two primary uses of hashing functions that we talk about. One is for storing passwords, and the second is for ensuring the integrity of a message. So basically what this means, so for storing computer passwords, if I have a password and I take a hash of that password, I can verify that when somebody puts in a password, it matches what they had put in as originally for their password. And the beauty of it is I don't have to store their actual password. And if somebody gets to that password file, since it's a one-way hash algorithm, you can't look at the hash of someone's password and be able to figure out what the original password was. It wouldn't be possible unless you use some kind of brute force attack and things like that, which we talked about earlier with these various threats and attacks. So that's one usage. The second usage is to ensure message integrity, which is what I talked about in the previous presentation when I showed you a message for that credit card company that I modified a couple words. And if the credit card company was smart and they did an MD5 hash, they would be able to tell that I had changed the original document because the hash would not match. So it produces a unique value that corresponds to the data that's been entered. So that's where we get that signature, and that's what they're talking about there. So the hash value is also reproducible by anyone else running the same algorithm against the same data, which means if I use some software that can do an MD5 hash, you can use any other software and also do an MD5 hash, and we should get exactly the same ciphertext when we take a hash of the exact same file. So anybody can verify the integrity of a message using the same algorithm. And then in this presentation, I give you a little bit of a example of how that might be done. So a collision attack is used to compromise a hash algorithm. So how does this happen? It's when an attacker finds two different messages that have the same hash value. So it's a very difficult attack. This is not something that's easy to do. You have to generate separate algorithm that attempts to find a text that will hash to the same value of a known hash, and it must occur faster than simply editing characters until you hash to find the same value, which would be a brute force type of attack. So hash functions that suffer from collisions lose integrity because somebody could present some other message as, having the same fingerprint as another message. So an attacker that can make two different inputs hash to the same value can trick people into running some malicious code. So a pretty serious attack, although these attacks are very rare. They're also very difficult to do. So they're not common, but they could happen. So it's certainly something we have to be aware of. So next, we're going to talk about some of the hashing algorithms we have available to us. SHA is one, which stands for the Secure Hash Algorithm, and it refers to 4 hash algorithms that are published by the NIST, which is the National Institutes of Standards and Technology, and the NSA. So you can refer to FIPS Standard 180-2. So it applies compression function to the data input. So it sets up to 2 to the 64 bits or less, and then compresses it down to a smaller number of bits. Most algorithms use block mode to process data to create the hash. So in other words, we talked about block versus stream in a previous lecture. So hashing algorithms use blocks. So what does that mean? Basically, you're taking a chunk of data. So let's say we've got a file that's 1,400 bits long. So we would break that file into 3 parts, and each of those 3 parts would contain 512 bits. Now you might be, or 512 bytes rather. So you might be saying, well, gee, Brian, 1,400 doesn't evenly divide into 512. One of them is going to be a little bit smaller. Well, we have to pad that one with zeros. So we pad that one with zeros in order to make them all evenly sized. And then we do some compression, and then it processes those blocks, and we end up with our, with our hash. There are 4 variants of SHA. There's SHA-1, and your book talks about SHA-256, 384, and 512. So SHA-1 was one of the more secure hash functions, but it has been found to be vulnerable to collision attack. It's not common, and I wouldn't run away from SHA-1 just because it's vulnerable to a collision attack. It is very, like I said before, it's very difficult to do, and they're not very common. So for most purposes, if you're doing VPNs and things like that, I think SHA-1 can be trusted. But there are longer versions that we refer to as SHA-2. So those are all the other ones, SHA-256, 384, and 512. So they have a longer hash result, so they're more difficult to attack with these collision attacks. But it's going to require more processing power for SHA-2. So that's one reason people, I think, have stuck with SHA-1, especially when you're doing, networking with VPNs and things. You want things to be very fast. And, things are happening so fast anyway, it'd be difficult for somebody to carry out these collision attacks successfully. So we're not too worried about that stuff with SHA-1, but certainly something to be aware of. So message digest is the other algorithm, or the MD. So it's a generic version of one of several algorithms that are designed to create a message digest or hash from data input into an algorithm. MD algorithms work just like SHA. So they're very similar to SHA. So they use a secure method to compress the file, just like we did with SHA. And they're going to use the blocking mechanism and all that stuff that we talked about. So all that stuff basically works the same, but it's a different algorithm. There are 3 that are common, MD2, MD4, and MD5. So MD2 was developed in 1989. So it takes data of any length and produces an output of 128 bits. It's optimized for 8-bit machines. I don't remember the last time I saw an 8-bit machine. Even our cell phones, of course, are far more than 8-bit. They're 32-bit processors now. So MD4 came along about a year later, and that was optimized for 32-bit computers, which of course is, even in 1990, that was the state of the art, was 32-bit. It would be unusual to find an 8-bit computer in 1990. So it's a pretty fast algorithm, but it is still has some vulnerabilities that had to get fixed. So that's where MD5 comes in. So MD5 is a much better algorithm. It's much more susceptible to some of those attacks that were found in MD4. You very rarely will you see anybody use MD2 or MD4. And in fact, MD5 is still in pretty common usage. Even though it's a rather old algorithm. You can see here it was developed all the way back in 1991. But it's still pretty common today. So MD5 is still used a lot. It certainly is not as secure as SHA-2 for sure. Not even perhaps as SHA-1, but it's very fast. It's very simple. It's easy to implement. Almost every programming library has MD5 included. There's always an algorithm, even in, database languages and things like that. So MD5 is readily available. So it's still very common to use MD5. And I think most people aren't too worried about these collision attacks with MD5, even though it's a little bit easier to do those types of attacks. So like I said, it's still very common, MD5. The other one, which the other algorithm we have is NTLM. I won't read all these line items here, but basically NTLM was or is a hashing algorithm used by Windows. So it was proprietary to Microsoft, but I think later on they actually opened up this algorithm and made it, opened it up to public scrutiny. It's not, it's probably as secure as MD5. So it's not as good as the newer, the SHA-2 and things like that. But for sure, it's fairly secure. I think NTLM could be hacked relatively easily. In fact, it says here MD5 collisions can be computed in about 8 hours on a standard home PC. So in theory, NTLM, which does use MD5, certainly not as secure as SHA. So in summary, hashing functions are very common, and they play an important role in security. So we use it for storing passwords, signing messages, which we're going to talk about shortly, and maintaining message integrity, which I talked about. So computing a digest of the message, less data needs to be signed by the more complex asymmetric encryption. Next, we talk about key management. So the security of the algorithms relies on the key. So when we talk about all these different symmetric key encryption, we really have to keep those keys secure. So anything that have to do with exchange, storage, safeguarding, and revocation of keys is referred to as key management. So a key must be current and verified. We talked about that with session keys in the previous unit, and how if we both share something, it's not really a secret for very long, right? If you have an old or compromised key, you need a way to check to see that the key, or if the key has been revoked. So all that stuff is important for key management. So keys can be stored in many different ways, but your book talks about this, that newer PC hardware, and most of you probably have computers that include this, have a trusted platform module, or TPM. So it's a hardware-based key that many applications can use. So BitLocker, for example, uses TPM. So starting with Windows Vista and above, you could use BitLocker to encrypt your hard drive, and it used the trusted platform module, or the TPM. And it could be either a chip that's on the motherboard, or you can actually store the key on a USB drive, for example. And you would have to have that plugged into your computer in order to boot up the computer, because it contained the encryption key. And you could actually back up those keys. So I think there is actually a way to back them up when you use BitLocker. But it's just one example of key management. So we talk about symmetric encryption. These are all the different algorithms your book mentions: DES, triple DES, AES, so forth and so on. The first three on this list are probably the most common, and then the other are probably, the other five are much less common. But the first three you'll see all the time, especially if you start working with VPNs and things like that. So they're all over the place. So we're going to talk about these. I'll just very briefly go over most of these, but the other, so DES, which stands for Data Encryption Standard, was developed in the 70s, and it's adopted as a federal standard in 1976, so it is a rather old standard. It has been a common business standard for 20 years, so modern computing power has, and the problem here is that it's a very small key with DES. So you can see here the block size is 64 bits, so 64 bits of plain text gives you 64 bits of ciphertext, but it's only a 56-bit key length. That's a relatively short key length, 56-bit. And because of its short key, it's relatively easy to break this encryption. So NAST recommends using AES now, which we're going to talk about in just a few minutes. But between AES and DES, or before AES became a standard, we had triple DES or 3 DES. So it's either 2 or 3 keys, and it's multiple encryption. So you're taking the same message and you're applying DES encryption several times. So it gives you much stronger encryption, even using the weaker DES algorithms. So the longer key length makes it a bit more resistant to brute force attacks. The fact that it's encrypted several times also makes it a little bit stronger, but it's still not as good as AES. So here's an example of how DES or triple DES is actually implemented. You have your plain text. You use key A to encrypt it the first time, use key B to encrypt it the second time, and then use key C to encrypt it the third time. So you're taking encrypted data, you're decrypting it with key B, and then you're encrypting it with key C. So lots of steps here, but you're getting a much stronger encryption using this weaker algorithm, and it's based loosely on the same mathematics. So they didn't really have to have any major breakthroughs in mathematics to make DES more secure with triple DES. However, AES did require a major breakthrough in mathematics. Somebody had to create, and I believe this is known as Randall encryption before it was adopted as AES. But so it uses data. It uses 128-bit blocks, but could also be used with blocks of 192 or 256. It can have key sizes of 128, 192, and 256. Obviously, the better the higher the key, the more secure it's going to be. There are very fewer, if any, efficient attacks that exist against AES. Brute forcing it would be extremely difficult. It's a very powerful algorithm, so this is really the state of the art. The other one is CAST, which is an encryption algorithm that is similar to DES. So it is a little bit weak, but and you can see here there's some minor weaknesses that have been discovered. So you should use it, layered with other algorithms. But CAST I don't think is very common. I don't see CAST all that much. RC on the other hand is a little bit more common. So it was designed as a DES replacement, obviously prior to triple DES. 128-bit block sizes. So the keys can be 128, 192, or 256, very similar to AES. And then there's RC4, which is a stream cipher, which uses key lengths of 8 to 2048. Again, not as common as the other algorithms. Blowfish, which was developed by Bruce Schneider. By the way, highly recommend his blog. Bruce Schneider is a pretty well-known security researcher and cryptographic researcher. So he developed Blowfish in 1994. It's a pretty good algorithm. Runs well on 32-bit machines. It's strong when implemented with the full 16 rounds. So Blowfish is certainly a good option, but it's probably not as common as some of the other options we talked about. International Data Encryption Algorithm, or IDEA, released in 1992, so also relatively old comparatively. Block mode cipher using 64-bit block size and 128-bit key. It's fairly new, even though it's from 1992. But if you think about it, DES is all the way back from 1970 whatever. So it's susceptible to weak key vulnerability, but easy to mitigate by using stronger keys. So symmetric algorithms are important because they are comparatively fast. They have very few computational requirements when compared to asymmetric. So it's much faster and much more efficient than asymmetric. Their main weakness is two geographically distant parties both need to have a key that matches the other key, which we talked about in the previous unit. And if you have simple keys, they can be quickly brute force, so you have to make sure you're using strong keys. And it's certainly, a challenge is making these keys that are secure. So there's various ways to do that, though, which we don't really talk about in this course. But we can also, so secure key exchange can be an issue, but we can also mitigate that issue through asymmetric encryption, which we're going to talk about. So asymmetric encryption, which we talked about previously, is where we have public keys and private keys. So we're going to talk about a couple different asymmetric encryption standards: RSA, Diffie-Hellman, LJamal, which I'm not familiar with, and ECC, which is elliptical, which we talked about elliptical curves in the previous unit. So asymmetric encryption, invented by Whitfield, Diffie, and Martin Hellman in 1975, uses two keys instead of one. We commonly call this public key cryptography. So asymmetric, the other term you'll hear is public key cryptography. So you have a private key that is kept secret, a public key that can be sent to anyone, which I described in the previous unit. The security relies upon the resistance to deducing one key given the other, which again we talked about. So it typically works by using hard math problems. So this is where we talked about factoring, right? Factoring is hard, multiplication is easy. So a common method relies on the difficulty of factoring large numbers. So trapdoor functions are difficult to process without the key, but easy to process once you have the key. Computers can easily multiply very large primes with hundreds of thousands of digits, but they cannot easily factor the product. So that's basically how most public key encryption standards work. So they also form the basis of digital signatures, which we talk about later on. So RSA, which is named after these three guys' names that you see up here, was one of the first public key crypto systems invented from back in 1997. So this is, even though they've been around for a while, since 1975, the concept's been around since 1975, but 1997 is when we first get the first real public key crypto system. So it's used for encryption and digital signatures, uses the product of two very large prime numbers between 100 and 200 digits long and of equal length. While a simple algorithm, it has withstood the test of more than 20 years of analysis, so it's still pretty strong. It does not replace symmetric encryption because RSA is 100 times slower than DES. So think about that for just a second. It's 100 times slower than DES. That's pretty darn slow. So we don't want to use this for exchanging a lot of information. It's used mostly to exchange the symmetric keys. So most of these asymmetric is really used to set up that symmetric encryption later on. So Diffie-Hellman was created in 1976. The protocol is one of the most common encryption protocols in use today. If any of you guys have set up VPNs, you've probably seen the term Diffie-Hellman as one of the options for asymmetric. So when you're negotiating to create that key. The electronic key exchange method of secure sockets layer protocol, it's used in TLS, SSH, and IPsec. It enables the sharing of a secret key between two people who have not contacted each other before. In other words, Diffie-Hellman makes it possible for computers to automatically negotiate for a symmetric key. And that's really the purpose here of Diffie-Hellman. If you're setting up a VPN, what you're really saying when you use something like Diffie-Hellman is, I'm going to use this algorithm in order to negotiate to actually get the symmetric key, which I really want to use for my encryption. I'm not going to spend too much time talking about this algorithm. I don't think it's that common for both encryption and digital signatures, just like all the other ones. It's used as the U.S. government standard for digital signatures. It's been in use for quite some time, and again, primarily for digital signatures. PKI manages the sharing of trust using a third party to vouch for the trustworthiness of a claim of a certificate owner. So switching gears here a little bit, so we've talked about asymmetric encryption and symmetric encryption. Now we're going to talk about public key infrastructure, which is how can we trust the authenticity of a public key? So far we know that we can create a secure connection between two parties by exchanging public keys and using those public keys to encrypt messages between each other in order to come up with a symmetric key, which we can then use for the encryption. But as I described in the previous unit, what happens if two people exchange if two people are trying to exchange those public keys and one of them gets intercepted by a third party? How do I know if that's really the person's key to whom I want to speak with? How can I be assured that when I secure a message with a key, it's really their key and it's not somebody else's key that's going to then go and eavesdrop on the message and then send it on to that other party? So it allows different types of users and entities to be able to communicate securely in a predictable manner. In other words, we can vet those keys, and we're going to talk more about this in just a few minutes. So can you trust that key? So Katie, who is down at the bottom, she replaces John's public key with her public key. And then Diane, who's in the upper right, when she goes to look up the key for John, she really gets Katie's key. And then when Diane goes to send the message to John, she's really using Katie's key to encrypt that message. And then Katie intercepts the message that Diane sends and decrypts it, reads the message, and then re-encrypts it using the key that Katie has for John, and then sends the message on to John. John then gets that message and is able to decrypt it. Diane and John have no idea that Katie is in the middle mediating that connection between the two. So that's the important concept here. And this whole PKI thing that we talk about is how do we prevent that from happening? So the basics of PKI, they use entities called registration authorities, or RAs, and certificate authorities, or CAs. It works a little bit like the DMV. So if you think about it, when you go to the DMV, you get your driver's license. So once you have a driver's license, the DMV, in order to issue you a driver's license, now I live in New Jersey. In order to get a driver's license in New Jersey, you have to bring a tremendous amount of paperwork with you to prove that you are who you say you are. They have this, this 7-point ID system where they assign a point value to all these different documents that you have to bring in. So, you have to bring in an electric bill to prove that you live somewhere that's got your name on it. You can bring in your passport. You can bring in, all these different documents, but they won't accept just one document. It has to be multiple documents. So the DMV does a lot of work to make sure that you are who you say you are. And once they vet your identity, the DMV, they give you a driver's license. You can then take that driver's license and you can use it as identification when you go anywhere. And when somebody else looks at your driver's license and everything looks good on your driver's license and it looks like it's a legitimate driver's license, then they can be assured that they can believe that you are who you say you are, because they know that the DMV already vetted you. They already verified your identity. So you're implicitly trusting someone's identity because they have an ID from the DMV. It's very difficult, and you can certainly try to live in society without an identification from your local DMV in the United States, but it's very difficult. You can't even get on an airplane without valid identification. It's difficult to get on a train. It's difficult to cash a check or even to go to a bank and do anything. I mean, everybody wants to see your ID, and any ID that's not a driver's license just doesn't seem to work for anyone. Although a passport could also work, but even then, sometimes it's a fight with a passport, except for at the airport. So that's the important concept. So PKI helps prevent the man-in-the-middle attack by setting up these trust relationships. So digital certificates and public keys, roughly how this works. Diane validates the certificate. Diane extracts John's public key, and Diane uses John's public key for encryption purposes. So basically, John has a certificate that contains his public key. And when Diane sends a message to John, she's going to get that certificate, and she's going to extract the key from it in order to encrypt messages for John. So she's not just going to assume that that key belongs to John. She's going to use the certificate to do that. So how does a certificate work? Well, CAs are basically a trusted authority that certifies identities and creates these digital certificates. You can think of the CA as sort of like the DMV. They're issuing the driver's license. Digital certificates establish an association between the subject's identity and a public key. The private key that is paired with the public key in the certificate is stored separately. So all this stuff here on this slide basically supports how these certificate authorities issue these. So you have registration authorities. An RA is a PKI component that accepts a request for a digital certificate and performs the steps of registering and authenticating the person requesting the certificate. So anyone can request these certificates. You have to vet your identity through these RAs, and then they will issue you a certificate through a certificate authority. Usually, when you try to get a certificate, so anyone who's had a website where you try to set up SSL for a website, you usually have to go through this process. So you usually have to provide some proof that you're a real entity and that you are who you say you are before you can get issued these certificates from a registration authority. Your book talks about these three. Actually, your book does not talk about these three classes. So I will skip over this slide, but certainly something you can look at later. But in this course, they don't really expect you to know the. I should probably remove that in the one. Well, I'll leave it in there so you can see it, but certainly not something you need to know for this particular course. So steps for obtaining a digital certificate. So first, the user registers for a digital certificate. Some method is used to determine some random values, and then an algorithm generates a public and private key pair. So they use some algorithm, and they're going to give you your public and your private key. The key pair is stored in a key store on the workstation. A copy of the public key and other identifying information is sent to the CA. The CA generates a digital certificate that contains the public key, and only the public key. We don't give them the private key, of course. And the new certificate is sent to the user. So that's how we go through the process of getting a digital certificate. If somebody gets that digital, so if I'm trying to prove my identity and send my key to someone, I'm going to give them that digital certificate, and they're going to verify that digital certificate with the CA. So a local registration authority performs the same functions as an RA, but it's implemented in companies that have their own internal PKIs. So if you have your own, if you're not going to use the public internet for your as an RA, you can certainly do all this internally using LRAs, or a local registration authority. A certificate repository is a central directory of public keys and certificates that can be accessed by a subset of individuals. Usually this uses LDAP. I don't want to talk too much about what LDAP is, but this is something that's supported with Active Directory. So LDAP is certainly something you can enable, and most people do with Active Directory. So if a person wants to encrypt the first message to the receiver, the sender needs to find the receiver's public key in a certificate repository. So they're going to go to the certificate repository to get the receiver's public key. So if you use PKI and you do not automatically trust individuals that you do not know, so a third party that is trusted by both the first and second party is needed. So a user will trust certificate authority and download a CA's digital certificate and public key. Certificate authorities you trust can be found in your browser's list. So if you take a look in most of your browsers, you're going to see a list of certificate authorities that your browser trusts. So as long as a certificate is issued by one of these trusted authorities, then your browser should implicitly trust that website. And I'm sure some of you have seen that when you go to a website, it may not be trusted by default. So by default, it's going to warn you and say, I can't vet the identity of this site, or it doesn't match, what it's supposed to be, and they're going to warn you. So where are they getting this information? They're going to go look in the list of trusted certificate authorities. So steps for verifying a certificate. This is a pretty complex list of steps. I'm going to let you guys take a look at this on your own because I don't want to waste too much time, going through this in these videos. I try to keep these videos to 30 to 40 minutes, so I'm already over 30 minutes. So certainly you can download the presentation and take a look at this slide. So validating a certificate, these are basically the steps that you're going to take. So a digital certificate is it binds an individual's identity to a public key. So the idea here is that if you get a digital certificate for a user, that digital certificate is going to contain the public key, and you have a method to verify that that is indeed their public key. So this is again how we get around this problem of third party, of the man in the middle trying to intercept these messages because they can change that key. So certificate attributes, and by the way, I'll go back 2 slides just so you know. This does talk about X509. So X509 is the standard of the information and how these certificates are formatted. So the information that you will find in a certificate and how it's formatted, it's all in the X.509 standard. And these are some various fields that you'll find that are available to you using X509. So end entity certificates are issued by a CA to a specific subject. The CA certificate can be self-signed, although if it's self-signed, then some entities won't accept it because they won't trust you. Cross-certificate, these are used when independent CAs establish peer-to-peer trust relationships, and we'll talk more about this in just a few minutes. So certificate life cycles. Key certificates should have a lifetime setting. In other words, certificates don't last forever. They have to have some finite amount of time that they are valid. So shorter lifetimes limit the ability of attackers to crack them. Longer lifetimes lower system overhead, obviously, because you don't have to renegotiate and get new keys periodically. So shorter lifetimes are not as efficient, but they are more secure, just like everything else, right? The more secure it is, the less efficient it is. So certificate management involves registration, certificate and key generation, renewal, and revocation. And we have to have a way to identify when stuff is revoked. So renewal is the process of at the end of a certificate's lifetime, it can be renewed. So if the certificate has not been revoked, the original keys and certificate are used to provide authentication for renewal, or you can get a new certificate. Revocation is when a certificate can be revoked when its validity needs to be ended before its actual expiration date is met. So most certificates have an expiration date, but what if it's been compromised? Revocation can remove that certificate, so people won't trust that certificate. They're going to periodically check to see if what's been revoked. And that's done by maintaining a certificate revocation list, or CRL. So the CA digitally signs the CRL and then can distribute that to downstream systems. CRLs can be requested by individuals or pushed down periodically, but they can grow substantial in size as certificates are revoked. So updates may only be changes to the CRL and not a full list. A certificate might have an extension that points to the validating user to the necessary CRL distribution point. So you can use online services or online certificate status protocol. So suspension is when you want to temporarily suspend a certificate. So rather than revoking it, you can just say we're going to temporarily suspend the certificate. And obviously the idea is that sometime in the future you're going to start using that certificate again. Private key protection. So private keys, we always have a pair. It's a public key and a private key. We have to make sure that we protect the private key. The key size should provide the necessary level of protection for the environment. The lifetime of the key should correspond with how often it is used and the sensitivity level of the data. The key should be changed at the end of its lifetime. The key should be properly destroyed at the end of its lifetime, and the key should never be exposed in clear text. In other words, we should store our key encrypted, and no copies of the private key should ever be made. So we have to make sure we keep these, very close. The key should not be shared. It should not be. It should be stored securely. It should require authentication before it can be used. It should be transported securely. So in other words, we just got to be very careful with these private keys, because if somebody gets a private key, obviously they've compromised your encryption. Public CAs are already established and being used by many other individuals and companies. So that these are public certificate authorities. Some examples of public CAs that you probably have heard of is VeriSign, Entrust, and GoDaddy. I think everybody's heard of GoDaddy, and they are certainly a CA. You can also use in-house certificate authorities. An in-house certificate authority is implemented, maintained, and controlled by the company that's implementing it. So if you have Active Directory, you can use Active Directory as an in-house certificate authority. And it will implicitly trust those other certificate authorities that we talked about, like GoDaddy. But internally, we can use our own certificate authority. How do we choose? So each company is unique. There are many factors. It's not just a financial decision, but generally you would use public CAs because they already have the necessary equipment, skills, and technologies. You would use in-house CAs if you do not trust outside authorities. And you just want to keep that internal. So again, there's various reasons. I think for the most part, it's something that's certainly baked into Active Directory and Microsoft and all that stuff. So it's not hard to do it on your own, but it's certainly something else that has to be managed and maintained inside your network. So these trust models, there are several forms of trust models. There's hierarchical, peer-to-peer, and hybrid. And this really gets into that concept of transitive trust that we talked about previously, where if I trust, if I'm A and I trust B and C trusts B, then C should trust me implicitly because B trusts me. And that's kind of what we're talking about with these different trust models. So let's talk about, this is just an explanation of what I just told you about these trust models of A trusting B and all that stuff. But there are three. There's hierarchical, peer-to-peer, and then hybrid. So a hierarchical trust model is where you have a basic hierarchical structure that contains a root CA and then intermediate CAs, leaf CAs, and end entities. The root CA is the ultimate trust anchor for all of the other CAs. So there's no bidirectional trust that exists. It's all from the top going down. In other words, I have a root CA, I have an intermediate A and B, which then have leaf A, B, C, and D. So D trusts B. So leaf D trusts intermediate B, and intermediate B trusts the root CA. And then the root CA trusts intermediate A, and so forth and so on. So the trust relationships here all go back to the root. So the only way that leaf D can trust leaf A is through the root CA. They can't do that peer-to-peer. And let's fast forward to peer-to-peer. So a peer-to-peer model is one CA is not subordinate to any other CA. They're all peer-to-peer. They all trust each other. But the main drawback to this model is scalability. It very quickly grows out of scale. Now, we only have so many certificate authorities, that exist. So we can kind of do a hybrid of both of these in the public CAs. So in a hybrid trust model, two companies have their own internal hierarchical models that are connected through peer-to-peer model using cross-certification. So another hybrid configuration to implement a bridge CA. So here's an example where we have a bridge CA between these two hierarchical. So in other words, in this example, we've got three hierarchical trust relationships, but they're all peer-to-peer with one another. So those three roots all trust each other through the bridge CA as a peer-to-peer, but internally it's a hierarchical structure. And that's basically it. So that's this unit in a nutshell. I kind of went through that very quickly, about 40 minutes. I try to keep these presentations under 40 if I can. If you have any questions, let us know. And by all means, I'm going to post this PowerPoint. Will be in the shell in Blackboard. And I encourage you to download this and go through it a little bit slower if you need to kind of review some of the material. This does go into a little bit more detail than your book goes through. So certainly the level of detail that you find in your book is sufficient. But I tried to give you a little bit more information in here and present it a little bit differently than the book. I know encryption can be rather confusing, and it's a lot of stuff to cover. And this is probably one of the most difficult chapters, I think, in this course because of the complexity of encryption. But really what we're trying to do is make sure you're familiar with the vernacular and the tools and technologies that are available to us in the real world, but you don't necessarily have to understand all of the mathematics underneath all of this encryption stuff. So if you have any questions, let us know. Thank you for watching.